You know, our world is, well, it's messy, it's interconnected, and a lot of the time it's completely unpredictable. We're always trying to make sense of these huge systems, like weather or financial markets, that are just too big to wrap our heads around. So, what do? We build models. We create these little digital worlds in a bottle to try and figure it all out. But what happens when those worlds start to have a mind of their own?
And this is where things get really, really interesting. I mean, we build these simulations, right? We program in every single rule. We should know exactly what they're going to do. But what if we don't? What if a simulation could do something that genuinely surprises the people who made it?
So, check this out. There's this story from a game developer. He made a pretty simple system, a trap that spawns a single zombie. Easy enough. But he never, ever considered what would happen if a new zombie happened to be standing on that same trap. The result? This unintentional, unstoppable zombie-making machine that just completely buried the player. Now, here's the kicker. This wasn't a bug in the code. It was something else entirely.
And this kind of thing isn't just for video games. It is everywhere in the natural world. Just think about a flock of birds. There's no single bird who's the leader. No one has the master plan for that beautiful swirling pattern they make. Each bird is just following a few incredibly simple rules, like, stay close to your neighbors, but not too close. And out of those simple, local rules, this complex and unpredictable global pattern just emerges.
This is the big idea that scientists call emergent behavior. It's this almost magical thing where the whole system becomes greater and often way stranger than the sum of its parts. That big, high-level behavior, the zombie apocalypse, the flock of birds, it wasn't designed from the top down. It just bubbled up from the bottom.
And you know what? There's a name for systems that act this way. They're called complex adaptive systems, or CAS for short. And they're everywhere, filled with individual agents. Could be birds, could be zombies, could even be stock traders. Each one just doing its own thing, but their interactions create the crazy, unpredictable behavior of the entire system. All of these systems have a few key fingerprints. They're all made of tons of interacting parts, and they are incredibly sensitive. You've heard of the butterfly effect, right? Well, that's exactly this. A tiny little change at the very beginning can lead to massive, completely unexpected results down the road. It's what makes these systems so powerful and so darn hard to predict.
And look, this isn't just some abstract theory. We see these systems literally all around us. The entire air traffic control network, with thousands of individual planes all moving at once, that's a complex system. A hurricane, a terrifyingly huge pattern that emerges from the simple interactions of air and water molecules, that's a complex system. So, all of this brings us to the really crucial question. Why does any of this matter? I mean, who cares, right? Well, it matters because we don't just simulate these complex systems for fun. We use them to make critical, high-stakes decisions in the real world. For example, take a look at this. It's a military simulation called MANA, and it was used to test the U.S. Army's future force idea. This was a fighting force that was built around this super advanced, high-tech communication network. The whole point of the simulation was to answer a simple but absolutely vital question. What happens if that network starts to fail? The simulation just crunched away, running through countless variables. But one totally shocking finding just jumped out. And it all boiled down to this one single number. Yep, a seemingly small 25% drop in communication range didn't lead to a 25% drop in effectiveness. No, it caused dramatic negative consequences. The force didn't just get a little weaker, it completely fell off a cliff. That right there is a classic textbook signature of a complex system at work. But getting these models right is incredibly hard, and the cost of getting them wrong can be absolutely catastrophic. Think about the 2007 financial crisis. Banks were using this really complex model to manage risk, but that model had a fatal flaw. It was built on the assumption that a housing market crash in, say, Florida, wouldn't affect the market in California. It treated huge risks like they were small and isolated. Well, when that assumption turned out to be spectacularly wrong, the model blew up and helped trigger a global economic meltdown. It's the ultimate lesson, isn't it? If you're using the wrong map to navigate a complex world, you might just drive right off a cliff. Okay, so these simulations are obviously super important, but how in the world do you actually build one? Especially when you need to combine totally different models, like a weather simulation, a logistics simulation, and the combat simulation, into one big, coherent virtual world.
The huge challenge is getting them all to talk to each other. You've got simulations written in totally different languages, running on different computers, built by different teams. To make them work together, you basically need a common language. You need a universal translator for the digital world.
So in the world of big-time simulation, that universal translator is called the high-level architecture, or HLA. Think of it as a set of rules of the road for simulations. It's an open international standard that lets developers plug their individual models together into one massive coordinated simulation they call a federation. It pretty much works with three key pieces. First, you have the individual simulations. Those are the federates. Then you have the runtime infrastructure, which is basically the central telephone exchange that connects everybody. And finally, and this is the most important part, you have the federation object model. This is the common dictionary that everyone agrees to use, so when one simulation says tank, every other simulation knows exactly what that means. And don't think this is some dusty old standard sitting on a shelf. Nope. It's been changing and evolving for decades. It started out as a US military project way back in the 90s, but it grew to become an open international standard. And it just keeps getting updated to handle new challenges like web services and, with the latest version, the massive scale of cloud computing. So we've got the standard. We can connect the digital dots. But building these worlds is still a huge technical challenge. And as we're about to see, it's also a massive human one. Which brings us to the real cutting edge of how these simulations are being built today. Just look at this. This isn't about just banging out some code. This is the whole workflow for a single large simulation. It's this sprawling, kind of messy, very human process of gathering data, designing scenarios, quality control, analysis. Every single one of these bubbles represents a huge amount of work. So when you look at all of that, the complexity of the systems we're trying to model and the complexity of the process we use to model them, it brings up a huge question. How can we possibly do this better? How do we make this whole process faster, more flexible? Well, the answer, honestly, it sounds like something straight out of science fiction. We're starting to use artificial intelligence, specifically large language models, to automate parts of the process. We're literally getting AI to help us write the code for the simulations. Okay, so here's the big idea. Researchers are using AIs that can understand not just words but pictures too, to look at a high-level diagram of a simulation. The AI then automatically translates that picture into working code. It essentially creates these smart little traffic cops that stop the simulation from getting bogged down with irrelevant information. And the impact is just staggering. We're talking about speeding things up by 20 to 60%. That's huge. So our tools for modeling this messy world of ours are becoming unbelievably powerful. We can build these vast digital worlds, and now we can even use AI to help build them for us. But all this power brings us right back to one final, really crucial question. The simulations, they're getting better and better at giving us answers. But are we getting any better at asking the right questions?